In the first video, we looked at how we develop this formula for the slope of a tangent line, which is a difference quotient between 2 points, and then we say let's let h, the distance between the 2 points, approach 0. So now we're going to do a few examples of using this to find slopes of tangent lines, and then once we have a slope, we'll also have a point and we can write an equation. So for these two examples, it's asking us first to find the slope of the tangent line to the graph at the given points. So we have f of x equals x squared minus x at the point 412. So if we're at the point 412, that means our a value is the 4. So then using the formula from above, the slope of the tangent, so m, is equal to the limit as x approaches as h approaches 0, wrong formula, as h approaches 0 of, now I'm going to write it in function notation on this first one, not because this step is necessary, but because it's useful to be able to look back at our notes and figure out where our values came from. So I'm going to write it as, okay, let me scroll back up here so we can see it. Okay, so f of a plus h, remember we're plugging 4 in for a, so I'm going to put a 4 right here and right here. Okay, so f of 4 plus h minus f of 4 all over h. Okay. Coming down here equals limit as h approaches 0. And then f of 4 plus h means I'm evaluating this function for 4 plus h. So I'm going to plug 4 plus h in for both of those. 4 plus h squared minus the quantity 4 plus h. And then that's all the f of 4 plus h minus, and then f of 4. Let me move down just a tiny bit because I kind of am running into my other work there. Okay. Minus, and then f of 4, please use parentheses appropriately, is 4 squared minus 4. Okay, and all of that is over h. All right, so doing some algebration here, this is equal to the limit as h approaches 0. 4 plus h squared is going to be 16 plus 8h plus h squared, minus 4 minus h, don't forget to distribute that negative, and then minus, so this is 16 minus 4, which is 12, okay? And all of that is over h. At this point, when we simplify everything, any constant, anything that does not have an h attached to it should cancel out. If it doesn't, then you need to back up because you did something wrong with your algebra, okay? Once again, every term left over should have an h. And if I look, I have 16 minus 4 minus 12, that is 0, which means my constants did cancel out. Okay, so I'm left with 8h minus h, so 7h plus h squared all over h. Come down here. So equals the limit as h, come on, pen, approaches 0 of 7h plus h squared all over h. I'm going to reduce everything by h. Every term can't just cancel out one of them, but h has to come out of the whole numerator. So that and that becomes a 1. So limit as h, and if you want to combine a couple of algebra steps, that's fine. Limit as h approaches 0 of, I now have the quantity 7 plus h left over because my denominator is a 1. 7 plus 0 is 7. Okay, so following my equal signs back, the slope of my tangent line is 7. Okay. That's part A. Part B says to find the equation of a tangent line. Well, to write the equation of a line, we need two things. We need a slope and we need a point. Okay, so our slope is 7 and our point is 412. And since it doesn't tell us what form we need to write the equation of the line in, I'm going to do point slope because it's superior to all of the others. So point 412, slope of 7. So the equation of my tangent line is y minus y1, which is 12, equals the slope 7 times x minus 4, and I'm done. If Pearson tells you need to change it to slope-intercept form, go ahead and do that, but I don't care. I would stop right here, okay? Let's do another example. So here's our function, f of x equals root x. Our ordered pair is 1, 1, so that means a is equal to 1, okay? So the slope of our tangent line is the limit as h approaches 0 of, and again, I'm going to write function notation. So f of 1 plus h minus f of 1 all over h, okay, which would be equal to the limit as h approaches 0. Okay, so now I'm evaluating this function for 1 plus h. So I'm plugging the whole thing 1 plus h into that radical. So root 1 plus h minus, and then f of 1 is just root 1, obviously just 1, but we'll simplify in a second, all over h. Okay, here, in order to, if I plug in 0, I'm going to have root 1 minus 1, so 1 minus 1 over 0, 0 over 0 doesn't work, okay? But I know that I can do some algebra to rationalize that numerator, okay? When I rationalize the numerator, remember we are multiplying by the conjugate because we want to get rid of that square root. So I'm going to multiply the top and bottom of this fraction by the conjugate of this, which is root 1 plus h plus 1, you don't need a root there, over root 1 plus h plus 1, okay? And again, when we multiply, don't distribute your denominator. Leave that h out because you want to be able to cancel it. That's the factor that's causing the 0 in the denominator. And so don't distribute that through there. Leave it factored. Okay, but then my numerator, when I multiply two conjugates, I get the first term squared minus the second term squared. So that becomes, actually I can come over here so we can still, whoops, stop it. Okay, becomes the limit as h approaches 0 of root 1 plus h squared, root 1 plus h squared is 1 plus h minus 1 squared is 1 all over, again, keep this factored, h times root 1 plus h plus 1, okay? And then simplifying, that's the limit as h approaches 0. 1 minus 1 is 0, so I have h over, and actually, I'm going to reduce, well, it's got to reduce in the next step, h and then root 1 plus h plus 1, okay? I'm going to reduce the h and the h. These don't cancel like 1 and negative 1 to become 0, but they reduce to have, to be a 1 left in the numerator, and then I still have this. Now when I plug in 0, I no longer have a 0 over 0. I have 1 over root 1 plus 0 plus 1, which is 2. So the slope of my tangent line is 1/2, okay? Once again, part B says to write the equation of the tangent line. I need a point and a slope. My slope is 1/2. My point is the ordered pair 1, 1. So, come back over here. The equation of my tangent line, y minus 1 equals the slope 1/2 times x minus 1, and that is my tangent line. Okay, now, so we've been talking about how whenever you hear the term rate of change, okay, or slope, you should automatically think of the other one. Specifically with average rate of change, you should think slope of the secant and vice versa. But then instantaneous rate of change, you should think slope of the tangent. I'm going to add one more thing to that, and that is the derivative, okay? The derivative is the slope of a tangent line, okay? This is our technical definition for the derivative of a function at a point x. Okay, and again, when you hear one of these three things, you need to automatically think the others, and that is derivative and slope, specifically of a tangent, okay, and rate of change. Use a delta for change, or specifically the instantaneous rate of change as opposed to average. So if you hear one, automatically think the other two, okay? So this is the same thing that we just did. The difference is between this and the previous one is that instead of having a constant right here, we're just going to have the letter x, okay? And that's okay because instead of taking the derivative at a specific point like 1 or the derivative at 4 or the derivative at x equals a, whatever that constant is, here, we're just taking the derivative and leaving it in terms of x. In other words, the derivative of a function is another function, okay? But we can still have a variable or a constant there. I want you to understand that those don't have to be just one or the other. Like a derivative can be numeric if it's the derivative at a point. Like on this one right here, the derivative at 1 is 1/2. Okay, slope of the tangent, or we can have a function that represents the derivative for any value of x. Okay, so let's go through and do a couple more examples, finding the derivative function using, again, the same limit of the difference quotient that we did before, but it will be in terms of x. Okay, So here our function is x squared minus 5x. We're not using these points 1 and 3 right now. We're going to do it in terms of x, and then we will plug negative 1 and 3 into our derivative equation, or derivative function, to find specific values. Okay, so f prime of x, I'm writing full statements here, f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. Again, you can skip that step if you would like. Okay, it's a little bit bigger, which is equal to the limit as h approaches 0. So then if I evaluate my function for the quantity x plus h, I'm replacing both of these x's with an x plus h. So it's x plus h squared minus 5 times the quantity x plus h, okay? And then minus f of x, again, please be careful with parentheses. The quantity x squared minus 5x gets subtracted, all over h, okay? Now we have more algebra to do. So it's equal to the limit as h approaches 0, expanding that. And if I go too fast with the algebra here, stop it, look back, see, make sure that you understand it. If not, just ask me, and I can go through some of the algebra examples with you if necessary. So x squared plus 2xh plus h squared minus 5x minus 5h, don't forget to distribute the negative, minus x squared, and then again a negative gets distributed, plus 5x, all over h. Once again, if we are doing this correctly, anything that does not have an h in it should cancel out in the numerator. So I've got an x squared and a negative x squared. Those are gone. I have a negative 5x and a positive 5x. Those are gone. So when I simplify this, I have the limit as h approaches 0. And so I've got this term, and this term left in my numerator and an h in my denominator. I'm going to go ahead and factor an h out of, well, never mind, I'll do it on the second step. So I have 2xh plus h squared minus 5h all over h. Okay, now I'm going to cancel an h from every term in the numerator and the denominator. So gone. There's one h left here, and then that's gone. So then this becomes the limit as h approaches 0, and I have 2x plus h minus 5 left over. If h is 0, if I use direct substitution now, I get 2x minus 5. Okay, so this is my derivative. F prime of x, the function, is equal to 2x minus 5. Now, if I want to find the derivative at these 2 points, x equals negative 1 and 3, I just need to plug them into there. So f prime of negative 1 is 2 times negative 1 minus 5, which is negative 7. And then f prime of 3 is 2 times 3, so 6 minus 5, which is 1. Okay. If I had gone through and plugged negative 1 and 3 in for my x's, that would be fine. I would end up with these same values, but I would have to do all this algebra twice. So in some cases, especially if you're finding the derivative at more than one value of a or more than one point, it's easier to find the derivative function first and then plug your numbers in. Okay, let's do one more example of this. Okay, so my function is 4 over x. So my derivative, f prime of x, is the limit as h approaches 0. And I'm going to go ahead and skip the first step this time, but it's going to be f of x plus h. So I'm plugging x plus h into the function in place of h. So I have 4 over x plus h minus, move this down a little bit. Okay, minus f of x, which is 4 over x, all over h. Okay, as always, if I were to plug 0 in, I would get 0 over 0 because I'd have 4 over x minus 4 over x, which is 0 over 0. So I need to do some algebra stuff, okay? To do that, I need to get rid of these complex fractions, meaning fraction inside a fraction. And so I'm going to multiply the entire big fraction by the least common denominator of the inside fractions, which is the quantity x plus h times x. Those are two separate factors. All right, and I'm doing that on the top and bottom because I don't want to change the value of my fraction. Okay, when I do this, okay, if I distribute x plus h times x to the 4 over x plus h, the x plus h cancels and I'm left with 4 times x. So this becomes limit as h approaches 0 of 4 times x minus here 4 over x times this, the x cancels out and I'm left with an x plus h. Don't forget to distribute a negative 4 though. So negative 4x minus 4h, or if you want to write this negative 4 and then x plus h and distribute in the next step to be safe, totally fine. And then down in my denominator, nothing cancels because I don't have any fractions here. I am going to leave that h factored though, because again, we want to cancel out an h from the top and the bottom once we simplify. So h times x plus h times x. Okay. 4x minus 4x, that's 0. The non-h terms disappear, which is what we want. I have a negative 4h and an h down here. I'm going to reduce by h. So I'm left with the limit as h approaches 0 of negative 4 over x plus h times x. Plug 0 in for h now, and I have negative 4 over x times x, so x squared. So my derivative function is negative 4 over x squared. Okay? And then the last part, I'm plugging negative 2 and 1 into that. So f prime of negative 2 equals negative 4 over negative 2 squared, which is negative 4 over positive 4, so negative 1. And then f prime of 1 is negative 4 over 1 squared, which is just negative 4. Okay, let's look at one more example here. We are, let's see, yeah, just 2 parts here. We are looking at the volume of a cube written as a function, f of x equals x cubed, where x is the length of each of the sides. Okay, so length, width, and height are all the same on a cube. Okay, for part 1, and we're going to use our calculator for this part, we're looking for average rate of change. Remember, average rate of change, we think slope of the secant. So we're finding the average rate of change as x increases from 4 to 4.1, and then again from 4 to 4.01. All right, so for the first one, we're going to do f of, so I'm just doing slope between 4 and 4.1, and then I'll repeat it for 4 and 4.01. So f of 4.1 minus f of 4 over 4.1 minus 4, okay, which is going to be, okay, now since my function is just x cubed, I'm just going to type 4.1 cubed minus 4 cubed. If you want to plug this into your function and then evaluate, you know, like evaluate y1 at 4.1 and at 4, you're welcome to do that, but it's not a very complicated function. So I'm going to do the quantity, I'm going to do it all in one step actually. So I'm going to do 4.1 to the third. Whoops, actually, sorry, don't close the parentheses there. 4.1 to the third minus 4 to the third. I need parentheses around my entire numerator, okay? And then divided by 4.1 minus 4, which is just 0.1. So I really don't need parentheses there because I just subtracted in my head. Okay, which gives us 49.21. Okay, and let's look at our units. This is a rate of change of volume. So this is going to be in inches cubed. This is a weird one. It's actually inches cubed per inch. Okay, so but this means as the side length changes in a number of inches, we end up with a cubic change in inches, our volume. So that's actually inches squared, but that's okay. We don't really need the units so much on that one since we know it's just a change in volume. Okay. And then for the second one, we're going from 4 to 4.01. So again, average rate of change is slope of the secant. So f of 4.01 minus f of 4 over 4.01 minus 4 is, and then back to my calculator. And I'm going to repeat that. So 4.01 cubed minus 4 cubed, which is 64. I could just put 64 there. Okay. And then that whole thing is divided by 4.01 minus 4 is just 0.01. And we get 48.1201. Okay. Now, the second part says find the instantaneous rate of change of the volume with respect to x when x equals 4. So we're looking for instantaneous rate of change, means slope of the tangent or derivative. Okay, so we are looking for f prime of 4. That's what we're trying to find. So we could find f prime of x if we want, and then we can plug 4 into that, or we can just go ahead and do f prime of 4 and start with 4 as our a value. Both of them are going to get us to the same spot. So I'm going to write it as f prime of 4. So f prime of 4 is equal to the limit as h approaches 0 of, again in function notation, f of 4 plus h minus f of 4 all over h, which is, again, correct limit notation. Limit is h approaches 0. The limit stays on there until we've used it, okay? Meaning until we get to the point where we replace the h with a 0. F of 4 plus h is going to be the quantity 4 plus h cubed minus f of 4, which is 4 cubed, or again, 64, okay? I need to expand this. Lucky for us, we just learned binomial expansion in the last unit. So this becomes limit as h approaches 0 of, and if you need to write it out separately, you can, but it's going to be 4 cubed, which is 64, plus 3 times 4 squared times h, so 3 times 16 is 48h, plus 4 times h squared, but times 3, so 12h squared, and then plus h cubed minus 64. Okay, and then that whole thing, oh, forgot the other. Oh, no, I have the minus 64. Yep, we got it. Okay, divided by h. Once again, everything that does not have an h should cancel, which 64 minus 64 does. So I'm left with 48h plus 12h squared plus h cubed all over h. I can factor an h out of that whole numerator, cancel it with the h in the denominator, and I'm left with the limit at 0. Get rid of that, get rid of that, get rid of one of those, get rid of that. I'm left with 48 plus 12h plus h squared, all of that is over 1. Now when I evaluate the limit, I plug 0 in for h, and I get 48 plus 0, which is 48. And that is our derivative, or instantaneous rate of change. If you chose to do this with finding f prime of x first, I'll go ahead and show you what you would get. F prime of x would be 3x squared, and then when you evaluate that at x equals 4, you would get 3 times 4 squared. 3 times 16, you would get 48, which is the same thing.